Very generally, last time I talked about this. I have a question for you. Just just think about it. When we refer to neural networks, we say artificial neural networks, and we also talk about here specifically. We talk about multi-layer perceptron model, MLP. So we have two circles, as if it's a diagram. We have two circles, and if I do this, it's kind of cute, but that's not the point. So we have a bigger circle and inner circle. Which one do you think is the ANN? Which one do you think is MLP? What is ANN? Yeah. So which one is which? Anyone?
MLP is the outer circle, and ANN is the smaller one.
Any rationale?
Because of the multi-layer function on MLP.
Okay. Multi-layer. Wait, hold on. Multi-layer. MLP. Multi-layer. Hold on. Right. Multi-layer MLP. Yeah. Multi-layer perceptron. Actually, it's the other way around. Because artificial neural network is such a broad term. Some of the neural networks don't belong to the term MLP. It's not even perceptron. All kinds of tweaks and changes that make them an entirely different species of neural networks. But artificial neural network is essentially saying it's a neural network, but it's not the one that lives in our body. I mean, the one that lives in our body is neural networks. That's a real. That's biological neural networks. But artificial is, of course, simulated. It's man-made, right? So that essentially speaks to all the AI or sophisticated AI, basically. So that's ANN. And a lot of times we don't even say ANN, it's neural networks. We know that refers to artificial neural networks, So just to clarify, multi-layer perceptron mostly refer to, that's the beginning of neural networks. But now when we say multi-layer perceptron, typically refer to shallow, not very deep, at least 3 layers, but shallow neural networks that have fully connected layers. Fully connected, right? No unit is disconnected. Every unit is connected in a tight network. But that's only the beginning of the process to try to imitate biological neural networks, because the real animal brains, especially primate, animals with advanced brains, including humans, have billions of neurons connected in a very long chain. I guess that's all we can say. We don't know too much beyond that. And I think a neural chain and neural networks in actual I guess observation. I don't know about that, but I think the level of intellectual quotient IQ would probably be related to how long the neural cell chains in the brain are. And I guess brain damage refers to like Alzheimer, refers to or is somewhat related to damaging of the long chains, and disrupting the storage and flow of information. But hey, I'm no expert. So yes, and neural networks is like an infant to try to build the ultimate sophisticated AI, and we're still at infant level. The amount of intelligence that a sophisticated AI as of now, state of the art neural network can do, probably is like a monkey, or maybe not as much. And it's highly limited skill sets, and it's isolated. One time can do one thing, but certainly not as intelligent as a monkey, but on a very particular task, maybe. Self-driving cars cannot handle very complex situation, or at least, can't make a decision of stopping or I guess disconnect, require intervention. That can do, require human intervention. System disconnected, humans take over. That can do, but I guess a middle schooler can do as good as that and much beyond. We can we can ask questions, and based on the questions, we can learn furthermore. And we can observe other humans make decisions, and we can learn. Neural networks cannot do that. There are silos. You feed examples, you try to narrow the error space, it can try to improve, but there are always these controversial situations where questions can be asked, and AI will struggle, right? Say, for self-driving cars, there are tons of videos online of beta testers, right? So a very puzzling situation would be that a beta tester of a Tesla self-driving software have clearly experienced this road condition before and reported the error. And maybe through an update, the car did well once, but the next time the car didn't do well, failed again. And because of slight changes in road conditions, traffic and pedestrian, and even the car will make mistakes on road segments that it did well before. So how could that be? Clearly, driver is frustrated because it seems to the driver that the car did well before, and the road condition has been reported. the company can easily train on them and do better. Because there's a gap. There's a conflict between what you should do and what the car did. And if it's reported, if it's provided to the neural network as training materials, it could learn. Yes, potentially it could learn. But the thing is, you should not expect AI to do perfectly and also adapt to different situations. It's not realistic. And also, in controversial application areas like self-driving, some of the aspects are subjective. Let's say, how aggressive should you be in driving a car? In terms of how much tolerance is needed in waiting for the other cars, right? Different people have different opinions. And the company has to, sacrifice one aspect for the other. Maybe safety should be prioritized, and other aspects should be sacrificed. And also, people's opinion is a continuum. You can only pick a point and disappoint. I mean, satisfy these, but disappoint the others. That's two things. But also, company also has a bottom line. It feels as if PR issue is as important or more important to the company than trying to solve all these situations. Company has to be aware of the PR issue, than others. So, and clearly, beta drivers don't know what is overfitting, clearly. So, if a situation is reported on this car in this situation, he expects the next time update should fix it. But this is not the only issue here, right? And if it adjusts too well on this car in this condition, it sacrifices generalizability, as we talked about. So there's always going to be some mistakes or lack of perfection, if you will. And it's not like, past failures has to be fixed or past imperfection has to be fixed. It's not the case. Otherwise, that's customization. You can do customization, actually. And this car is more aggressive to you as a driver, but less aggressive to other drivers. That you can do, but the company is not at the stage where they can do this because more aggressiveness means more accident probability. One accident will kill this company, will kill this program. So it's not gonna happen that easily. So, in real life. But anyway, and for neural networks, there are different ways of describing them. Black boxes, a lot of times it's brought up, but the purpose of this course is to, after you finish this course, you can confidently say, it's not a black box to me. And whatever whatever the process is that's happening in the black box, you'll be able to understand. So that's the purpose of this course. Whatever the actual neural network learning process is for the state-of-the-art models, you can put them into different, you can put different parts into different labels. And I think you can kind of understand how, at least there's a forward process. There's a forward prop and backward prop, always. It's like, so at least you can have a way of understanding one level deeper into the process, no matter what the sophisticated algorithm is. And it's artificial to the end. So I talk about this a lot. These notations I'll keep referring to. In fact, in homework, we'll ask you to, adapt the codes on critical pieces of information, such as MD. What are these numbers? Based on the particular network structure. Like, there are 25 input features. We need 9 hidden units. We have 2 output units. Where do you change in the codes for that to train a model that fulfills to that requirement? That requires you to be familiar with the structure and connect that with the codes and the process of learning. We have 3 layers, and throughout this course, this is how far we will go. This is the most complex structure we will deal with. We'll change around the M and D, but we will not change T, and we will not add another layer. But after you understand this process, it's already very tough. After you understand the process, you can add a second layer. So that becomes K1, K2, D1, D2. You can add another layer. You can add more layers as long as it's fully connected. Then it just, the forward prop has more steps. The backward prop has more steps. That's it. You can reasonably imagine you'll be able to build the network from scratch. In that situation, it just takes more time and be more careful. Which 2 layers are connected? Which activation function are you using from which layer to calculate the error propagation for this layer? So that requires more care, but it's doable. And 3 layers is the most fundamental starting point for you to be able to do those. And after this, you would have nailed, I guess, all the territories in fully connected neural networks. You can go very complex, very deep. But going deep doesn't mean model is more capable. It comes with downside, more overfitting, more likely to overfit. Training time increases exponentially, and most of the time it's overkill. And then you hit a bottleneck, right? You hit basically a bottleneck that increasing the capability of the model doesn't help you solve that problem. And a lot of times you need a better designed model, which then, CNN might be a better model in that case. So then you'll move on to learn a new kind of neural networks, right? Any questions? Okay, process model overlay. So the forward prop has 4 steps. Backward prop also have 4 steps, but each of them have little steps, and each little step has mini steps. So you can see that complexity. But after you've gone through once, twice, 3 times, you kind of see that pattern repeating each other. And at the high level, it's the same logical process with logistic regression. Forward prop, you always calculate net input. Net input is calculated by using 2 components. That's the same. And then you do activation. That's logistic regression. With neural networks, you just finished the hidden layer. Now it's time to do the output layer. Then you do another net input. And then based on that net input, you do activation. So you know, net input and activation doing twice, each for one layer. Same process. But you do not do net input of the two layers at the same time. Why? Why not? The second net input requires the activated value of the previous layer. So you have to do net input activation and then net input activation. Otherwise, you're skipping a very important step. So this cannot do. But interestingly, when you do the backprop, you can kind of do this interlate. You know, you don't have to do one backprop entirely and then move on to the other layer. But you can calculate components such as error for the output, for the hidden together. And then do the next step of backprop for the two layers together. And then do the next step for both layers together. It's kind of twisted, but that's the way it goes. All right, ready for more specifics? Just don't fall asleep. Anyway, if you're into these kind of things, it's very, you know, it's intriguing to me because I have this tendency to, you know, to know why it is this way. So, and I can see, you know, I can see symmetry, I can see patterns, or at least I think I see the patterns, because it worked, you know. So if you see that and you enjoy that, I encourage that, you know, try to follow. Okay, with the notes and with the exact codes on there, I'll be flashing different parts of these when I talk about these. So if you have it on your screen, better also look for it. So do a practice run. I will not do the coding, actual coding particularly because you can see that in the video. Our video is better. You can see the exact codes, but I'll show particular parts when I have to. Overall process, you have forward and backward, and then calculate costs, save the costs, and move on to the next epoch. Same thing for the logistic regression. We have forward prop. We don't have hidden, but you can think of hidden as the logistic regression, but we don't have output then. So we have this one time we have net input activation, and then we move on to backprop. For backprop, we calculate error, only the output layer. We don't have this. We'll calculate gradient. When we calculate gradient, we only have one gradient. Let's say we have this, we don't have hidden, and we only have weight. We don't have different gradient for bias. So that's, you know, tick marks shows what's in logistic regression, right? And then we do weight updates, only up layer. We do have weight update for weights and bias. We keep them in the same matrix, same vector. We calculate the weight update in 2 steps. If you remember, we do a slicing and we do the one element replace. But here they are separate. So the steps are slightly different. I'll explain more details, and then update the weight is 1 step. 1 step, no difference, and no difference. So, you know, if you remove those other parts, then what remains is the logistic regression. You're putting these more additional steps, that becomes neural networks. Cost and score is after update the weight, you do a one forward prop. You know, you populate the information with the updated weights, and you calculate the costs, and you do a prediction, decision making. That's the same. Right. The demonstration uses the same. I think that's the same data set. The credit card default problem with 6-month data set, 6-month data, and some customers default and others don't. Okay. So, yeah.
How can we decide how many hidden layers are going to be enough for our?
Good question. We tend to include too many most of the time without realizing. And it's not easy to realize because let's say you train a network and it didn't work very well. It didn't learn. You know, when you observe the I guess it does learn and become overfitted to the training set, and there's variance. You know, accuracy on the training set versus the evaluation set is different. It does learn, but it's kind of hard to know. Is it because of the size? Is it because the size is too much? Typically are. I would say if you have a data set of 10,000 records and typical number of input features such as 20, 10,000 rows, 20 columns after pre-processing, and a 3-layer neural network with 6 hidden neurons, that's almost for sure more than what you need. That's almost for sure. So adding another layer typically doesn't make it better, but you can try. Always. I mean, even if you, it's like it's wrong, but you're just gonna do it and see the result, and there's no harm, right? Better, I guess, better wasting time than regret that you haven't tried. But that's most of the time. It's not absolutely for sure correct. So better try it, especially when it doesn't cost too much time to try it. So have a purposefully diversify the range of models and try them in a systematic way and then compare them. The only downside would be don't try too much, because even if it's overfitting, when you try too many models, the chance that one of the model just got lucky on doing well on both the training and evaluation set is higher. The chance of getting a lucky model that works just perfectly for this data set, even if we have cross-validation, is higher than when you have a test set. It still fails. That's possible. So just don't try too much, like 1,000 models. Don't go there. 10, 15, that's still reasonable. Out of the 10 or 15, choose the best one based on the validation set. Okay. For less complex problems, especially for non-NLP problems, non-textual problems, you don't need more than 2 layers of neural networks. That's basically. Yeah. But NLP and computer vision requires a better models. But if you use fully connected, it can still do it reasonably well. But you can add a few more layers. Computer vision has much more information over there, much more features. Tens of thousands of features. That's what a picture includes. When you flatten the pictures into pixels, that's how much information is included in that picture. It looks simple, but that's because we are good at it. Computers are not. So in that case, it's a lot of data. It's a dimensionality is a big issue over there for pictures. So you need a bigger network. for our business data sets, it's a toy for the network. So it's very easy. Hopefully that answers the question. Yeah, and for the projects, you probably don't need more than 2 layers. So, okay, so basically I talked about this. When you do the forward prop, you can think of it as 4 steps, but 2 steps being repeated. You do the net input on the hidden based on the inputs and the weights. This weight, we denote it as weight of the hidden that goes with the hidden layer, right? So we use the input data and weight of hidden to calculate net. Net input, or do I use Z? I think I use the Z of the hidden. And then you do the activation. Activation, we use sigmoid function, and that becomes A of the hidden, activated value of the hidden. So that's 2 steps. 1 step, 2 step. That finished the first one. And then you do the output layer. Calculate Z by using the activate value of the hidden. Calculate Z net input of the output layer. That's step 3. Based on that, do another activation. For now, we use sigmoid activation as well. Later, we'll optimize that. For now, we use that. Do step 4, which is activation of the output layer. So because this process is so mechanical and predictable, and it uses parameters that are so, kind of step by step, you can create a custom function just like sigmoid activation function. You can put all these steps, define the input and the ultimate output. You can put them into a function, and every time use that function to do the forward prop in 1 step. 4 steps become 1 step. That's part of the homework. And also the slides demo. In fact, I'll show that. In the slides demo, it's a bit slow. So after you do the pre-processing, that's the structure. We have input space is 24. Number of hidden neurons is 7. Step 1, net input of the hidden. Step 2, activation. I'm already using the sigmoid function, which includes a clipping feature, right? But that you can omit that. That's not critical. Activation is a critical step. Step 3, net input of the output. Step 4, activation of the output. And all of these are single line step. You put them into 4 lines, make a function. You take input from the training set, or no, you take input from the X data set, the features. You return, you calculate the activation of the output. You return that. You also return the other 3 because backprop uses some of these. So you better not calculate it again. Because you have calculated, you return it. You can just disregard them sometimes. I'll point that out. So return all of these. Next time when you use that, I think, where do I show how to use that? So calculate cost. When you updated the weights, when you do the forward prop, this is the function that was just defined. Instead of doing 4 steps and is more error prone, you can have typing errors, use this 1 step. It takes the X data set, returns 4. In forward prop, to make a prediction, you only need the activation of the output layer. So you discount the three others, and you only name the last one so that you can use it to calculate the cost. So that's the way to do it.
Professor?
Yeah.
Can you explain that last part where you said in forward prop you need to only mention A underscore out, that is activation output, and not the other three?
Oh, why do I not need the other three? Right. So, first of all, you can do that, right? That part I understand. And let's see. Here, I only need the activated value of the output layer because that's the ultimate result I need in order to calculate cost. Based on the cost formula, I only need the ultimate result. I don't need the middle steps. These are the middle steps. Using underscore essentially means I have, I know I mean, use the underscore means to discard them basically, to get lost, get lost in the memory. But I only need the last one. And based on the position of the four parameters separated by the comma, a program knows which one to assign to that. And this order, I mean, it doesn't matter. It doesn't mean A of out has to be the last one, but this is defined by us. In our definition, we return the A of the output as the last one. If you move this to the first one, you need to put that receptor to the first one, right? That's the way. But later we will do this again, but we need something else. We just don't need all of them, but we need something else. We'll get there. So the forward prop, easy enough, right? So let's talk about the backward. Back prop, same logic, gradient descent, right? Try to inch closer to the optimal model. It's just the solution is much more complex. We have how many more parameters? We used to have, let's say, M is 15. So we used to have 15 parameters plus bias. We have 16 parameters. That's it. And right now, if we have, let's see this, well, structure, and it's hard. So if M is 15, but D is 7, now we have 15 times 7 number of parameters. And we also have that bias. Number of bias is equivalent to number of D. So plus 7. So it's like 16 times 7, right? Of a number of parameters. And we also have these. So we have D times T. And plus, I guess, D times D plus 1, because that's bias. D plus 1 times T, additional parameters for the output layer. So that is way more complex. So backward prop is more challenging. To understand this part, so I didn't show that I didn't show the codes to calculate or I showed some, but I didn't, talk about these particularly, like, it's the dot product between train and matrix, X train dot weight matrix of the hidden, because I think that these are pretty straightforward. You can review them in the slides demo, but I'll focus more on these backprop. Okay, so backprop, the first big step is to calculate error, as well as error propagation to the hidden. Error of the output layer is easier. Let me show you what was on logistic regression. So after you have calculated Z, net input, you do the activation. This is sigmoid with a clip, this entire bubble, think of it as a sigmoid function. After calculating the sigmoid function, you get an activated value. Now, then you proceed to calculate the error. And for logistic regression, error is simply a subtraction. There's only one neuron, so there's only one step. And over there, remember, error is defined by the gap between your prediction and the ground truth. So it's always ground truth minus your prediction, right? A positive error means it's not big enough. A negative error means it's overshooting, like that. But in neural networks, we'll switch things around. It's kind of, I guess, add more sauce to it for some other reasons. So there, and for the output layer, that almost remains the same. So the output layer, which is mini step or little step 1.1, to calculate the error, which is where error of the output. Error of the output is you subtract the activated value. This is activation function. This is generic symbol to, you can change the function. Right now we're using sigmoid. The sigmoid activation function of the net input from the output layer, that's the output. Subtract the ground truth from the activated values in the output layer. Output layer is close to the ground truth. It's making the last step of prediction. That's why you directly subtract the ground truth. But notice that we switch around the order. So that makes the error reversed in terms of the sign. Right? If the error now is negative, it means overshooting. But previously, negative means not good enough. Wait, hold on. If it's negative, it's not enough now. But previously, negative means overshooting. Overshooting means, let's say, ground truth is 0, it's negative, but your prediction is 0.7. That's overshooting, that's too much. Well, overfitting is not regarding one prediction. Overfitting is the overall assessment that the predictions are fitted too much to the data set. It's two concepts. Overshooting here means the prediction is wrong. That's it.
But in either case, the predictions are going wrong, right? Whether it's like, even if it's like, we are having a positive error or a negative error, we are having error in either case. So how is like one is overshooted and other one?
Well, I guess that's not important. So, so let me not use overshooting. Let's say positive or negative error, right? Previously, we're subtracting the activated value from the ground truth, right? So positive error means prediction is not as high as the label, right? If the label is 1, prediction is 0.9, error is 0.1. There's 0.1 space to improve to get closer to the actual label. It's positive error. But here, if the active value is 0.9, actual label is 1, 0.9 minus 1 is negative 0.1. It reverses the sign. The absolute value doesn't change. Reverse align is purposeful. The reason is kind of, simple, is to make the next step easier to arrange. That's it. You reverse the sign here, and then you reverse the sign of the next step, it evens out. It cancels out. That's why. It's better to have 0 negative sign than to have 2 negative signs in 2 steps. That's the reason. I'll compare and show the difference. But at least on this step, you know the difference, right? It's reverse position. But the calculation is the same. You subtract one from the other. That's the error. On the output layer, that's it. So the first sub-step is done. But the second sub-step of the error step is more complex, because that is for the hidden layer. Remember, the hidden layer makes activations that feed into the output layer, right? So it's not directly, close to making a prediction yet. There is an output layer that makes another activation and net input and activation process, which leads to predictions. So, something is in between. How do you know the errors that are committed in the hidden layer? You have to propagate the error and distribute the errors through the output layer. That's a basic reason. So to calculate that, because the formula is so long, I have to separate them into 2 steps. And then after we have the first step, we then use that first step result to calculate the second step to have the ultimate. So this is for the hidden layer error calculation. There are 2 steps. The first step calculates something that we say it's the error derivative part. This is a derivative. And later in step 2, we use that derivative as part of that bigger formula to calculate the ultimate error propagation. If we can do it 1 step, of course, but it's getting much more complex. So it's easier to manage it in 2 steps. That's the reason. But then I'll explain why this is error derivative. What does that mean? And why are these terms included in the calculation for the error propagation for the hidden layer? That's the intuition part. So first of all, okay, error transfer derivative. Okay, let's say on this node, it committed an error of 0.6. If we assume this is a classification problem and the labels are 0 and 1, an error of 0.6 is pretty huge, 60% of confidence. It's a big difference, right? It's almost reversing the prediction label. So it's big. But the problem is we have 4 streams of information feeding into these errors. Which one is responsible? That's a tricky problem to figure out. We want to, if let's say this is bias. So for now, bias is not responsible for optimization. So there are only 3. Let's say 3 weight parameter is responsible for committing these errors. Let's say this one is huge. It's 90% of the percentage of the error. and this is very minor, and this one too. So you want that the error that's propagated here, hopefully it's 0.55, and here is 0.25. Together they are 0.6. So you want something to happen like that. And how do you decide, right? So basically the let's see, there's some derivative calculation going on that I'm not going to talk too much about, but the error basically, the error is a component that you use to calculate gradient, and the gradient is a slope of the cost function with respect to the current parameter. So some partial derivative is done here, and to calculate the error propagation of the hidden layer, it's sort of taking a partial derivative of the error term with respect to the hidden coefficients. So these hidden coefficients has some kind of role in deciding how much errors they are responsible for. And it's intuitive. Let's say if the W of this line is, let's say W, the coefficient with a standardized variable. Standardized variable has a range of -3 to +3. Most of the values fall into that. So, and the variance, the numbers are almost always very close to 0, so between -1 to +1. So the coefficient cannot be very large in a standardized data set. If the coefficient here is 1.2, but the other coefficient is very small, that maps with the error, the error responsibility. Bigger coefficients tend to be more responsible because it's making a big influence. We want to change it to smaller if that is actually where the error came from, right? So that's part of the intuition. And when you take the, let's say, so if the error of the ALP, you want to take a derivative, partial derivative, with respect to weight of the hidden. So this is output, it's this layer. Weight of the hidden is actually here. Sorry, this should be, I think it should be out. So it's related to the weight matrix of the output layer that propagates to the hidden layer. When you do partial derivative of function with respect to not directly that function, but some function that makes up that function, it's getting more complex. And there's chain rule, if you remember from linear algebra. Let's say simple example. What is that? 4x squared. If you take partial derivative with respect to x, what becomes? 4, you can write because it's constant. X squared, take derivative of x, becomes 2x. 4 times 2x is 8x. So that's squared term. But what if there's a function of z? There's a function of z. Let's see. Hold on. Let's do this. So x is a function of z. Okay. So, by manipulating z, you can get x. But how do you do that? It's unsure. It's a function. right? So now we change the problem. That function, take partial derivative with respect to z. It's, it's kind of, there's a middle step, right? So the way you do that is you will take that original, you will take the partial derivative of the original unit of symbol, and then you time the partial derivative x with respect to z. That's a chain rule, right? To decompose the partial derivative process. And so in this case, the first part is what we calculated, right? So it becomes 8x times this thing. So it becomes two part. And that partial derivative that we're going to calculate in the first little step is actually that. So that's why we separate them into two steps. And that's how you can see error is propagated through the layers. That doesn't help too much, but at least help a little bit on what's happening here a little bit. So that gradient, the error of the hidden two steps. The first step the first step is the activation derivative is here. So we're taking the derivative of the function of z with respect to z. And because the activation is sigmoid, the way derivative works for sigmoid activation is 1 over 1 minus z to the minus e to the minus z. That you derive that function, it becomes activation element multiply element wise multiply 1 minus the activation. That's very simple, very good. So you calculate this activation derivative to be like that. You have this, right? Activation of the hidden. What is activation of the hidden? It's the hidden layer after activation. And it is this one. You already calculated. Activation of the hidden. You use that to calculate the step 1 of the substep 2. You do this. At the code level, what is this? This is not dot multiply. But this is simply times. Activation of the hidden, which you calculated here. Activation of the hidden. So in this case, when you do the forward for training process, you actually need this. You need this and that, right? So you'll capture 2 instead of capture 1. You use that times 1 minus the activation of the hidden. You calculate, you get the activation derivative. And after you have the derivative part, you go ahead and calculate the step 2 is the error propagation for the hidden layer is somewhat follows the or is the rest of the complex formula is you take the error of the output. You take the error of the output. That's the total error. That's all the error you have in the model, right? The error between activation of the output layer and the ground truth. That's all the error you have. You're supposed to calculate a portion of that error and populate into the hidden layer. So multiply the total error with some kind of weight, mechanism, and this activation derivative is part of that. And this is the weight matrix of the output layer. Weight matrix of the output layer is this one. We said this one will dictate which unit of the hidden layer is more responsible. It traces back based on how thick that which of these lines are. This line is thicker, it will distribute more errors. So that's why it's here. Total error is here. The weight distribution is here, and the chain rule is here. All three components together, you have the error propagation. Okay, pretty complex, and I have no idea how this is derived, but I can explain it. That's what I can do. But several things to pay attention to. You have a transpose here, as with not here, but right. You have a transpose here. You have to do. Here, there's only subtraction on the output layer, but on the hidden layer, you have a transpose of the weight. Be careful. And this is also simply the star, the asteroid, to do calculation. But here it's the dot product. It's pretty complex formula. If you take a look at the codes, it's the error of the output layer dot product with the weight matrix of the output and transpose before you do the dot product, and times activation derivative that you calculate from the previous step. That's all. After you do that, that's you completed the first step of the backprop. That's all errors. Questions?
So there is a range of error that is considered good or considered acceptable?
It's just proportional, bigger or smaller.
Yeah. How does the model knows that this range of error we can move forward and you don't need to go back and do formula?
I'm a little lost.
So we calculate this error to understand that what kind of error is there in our data, right? So,
we calculate error in order to calculate gradient. Right.
So once we calculate the error and once we calculate the gradient, what does the model does with error? What does it do with the
once you have gradient, you calculate how much update you want to apply to the current weights. After you calculate weight update, you update the weights, and the model has learned something. The model definitely learned something, but to what extent is the something that the model learned is generalizable or overfitting? That's the problem we need to solve. The model cannot solve by itself. The model will always learn something from the data to the point that it will perfectly predict this training set, and then it will stop, right? Model cannot optimize the generalizability. I mean, based on the current setting, of course, you can have regularization. That can help, right? But based on the current setting, it has a mission. It's going to eradicate all the errors. It's just going to do perfectly. Well, that's what the model is trying to do, right? That's as simple as that, right? So in this process, it's very similar to linear regression. Right? It's just more capable. That's it. And so, right, so I explained this part, that step 1 of backprop is done. Now, the step 2 of the backprop is to calculate gradients. We have 4 gradients, 4 mini steps. We have 2 layers, first of all. We have the hidden and the output. On each layer, we have the weights and the bias. Each of them have gradient, different gradients. We only, for logistical regression, we used to have only one gradient. Why is that case? It turns out the gradient of the bias is not exactly gradients in the same way as the gradient of the weight matrix. But because we now have the weights and bias separated, it's sort of like an engineering process to simplify. Previously we have a vector. We have the first element as the bias, the second to the last as the weights. And we only have the gradient for the weights particularly. And when we calculate the weight update for the weights part, we follow one formula. When we calculate the weight update for the bias, we follow a different formula. But if we do that here, it's going to be too much to handle, too much to manage, basically. The process becomes kind of falls apart. Why don't we also define a gradient for the bias? And then once we have these four gradients, the way to calculate weight updates follows the same formula. So in that case, it's kind of easier, right? And it's kind of symmetric. But when you take a look at these gradients, it's in no way similar to the gradient of the weights. But, conceptually, it's kind of simpler. So that's one. So let's take a look. Gradient of the output layer would be, as well as gradient of the weights of the hidden layer will be very familiar. And we can see that it's very similar to the literature regression. So now, step 2, 2.1, 2.2 is for gradients. 2.1 is for output layer. Calculation of the gradient it used to be transposed negative first, negative sign, transposed x data times error. That's the gradient for logistic regression. Here, minus dot product, transposed x, and the error, right? So we have this minus sign. And when we calculate the error, we're doing this way of subtraction. So because we have more formulas now, we better remove this negative to make it easier and make it less error prone. But if we remove that part, if we remove this negative sign, we have to reverse the sign of one of these components. And better way is to reverse the error. So that's why when we calculate the error, we reverse the order previously. That makes sense? I said, why do we subtract ground truth from the activation value instead of subtracting the activation value from the ground truth? We reverse that so that we can eliminate the negative sign when we calculate the gradient. That's why. But other than that negative sign, the gradient calculation for the weight matrix are the same. Transpose x for the current, transpose x that feeds into the current layer and times the error. But the issue is for the output layer, the data does not touch it. The input data, x data, does not feed into the output layer directly. What seems to be like the input data for the output layer is actually the activated value of the hidden layer. That's why we use activate value of the hidden layer transpose times the error of the output layer, and there's no negative sign. So that's clear, right? And then we jump to look at the gradient for the weight matrix for the hidden layer. It's going to be very similar to logistic regression. we have the train, we'll have the X data transpose times the error responsibility for the hidden layer that we calculated from previously, and we get rid of the negative sign. Everything makes sense. Now, for bias, we use something different. So for the bias of, for the gradient for the bias of the output layer, first of all, think for a moment about the shape of the bias. It's a vector. So bias vector is like this. If you have, let's say for the output weight matrix, it's like this. The number of rows, it's a weight matrix. It's not a square matrix. It's a rectangular. The number of rows will always map to the dimensionality of the previous layer. Previous layer has d number of dimensionality, so it's d rows. The columns will map to the dimensionality of the current layer. Is the upper layer is 2, let's say it's binary prediction. There are two output units, so it's d by t equal 2 in our case, most likely. D is probably 7. So this is the matrix. And what we used to only have a vector, right? We don't have the second dimension. We only have the first dimension to map to the previous dimensionality. And with the previous vector, the bias is, on the top. We add one element to the top, that becomes the bias. But when we have a matrix of like this, then our bias is like a vector that adds on top. And the dimensionality of the bias vector maps to the current dimensionality. One bias for one unit of the current layer, right? So be clear on that. And that's helpful for you to check your calculation, check the formula.
When you say that the bias is added over the dimensionality, so that will be like the matrix is D into T, right?
D to T, yeah.
Yeah. So there will be one more row to that.
Yes.
So it will be like vector plus D into T matrix, or it will be like D plus 1 into.
We don't actually stack them together. We keep them separate, but conceptually you can think of it as having one more row. Yeah, but we don't stack them. We keep them separate. There's really no need to. The only need to stack them is when you calculate stuff by using matrix. It's easier. If a formula requires both of them to be, put together, we will stack them and do the matrix calculation. Otherwise, we keep them separate. But conceptually, they map on that dimension. Yeah. And we intentionally put the bias vector. If they're separate, the bias vector can be a column vector. It's just the number of elements should be t, right? But we intentionally lie them down. We reshape them when we do calculate the forward prop. We do that just because that's easier for the matrix to work. But we don't stack them particularly. Gradient of the bias, right? So here, so how is gradient of the bias calculated? Gradient of the bias is a vector of 1 transpose, which becomes like flat. Dot product the error of the output. So what is it doing? So an error of the output is error of the output. The matrix that has T columns, there are T number of units in the output layer, and the number of rows is n. N is the number of examples. So this is error, yeah, because how do we calculate that? Error is the difference between activated value and the ground truth. These matrices always have n number of rows that corresponds to the training samples, but the dimensionality depends on that particular layer. So your output has T number of layers, which is typically 2 in our case. So this is n by 2. So if we have a vector of 1 transpose, vector of 1 corresponds to let's say the number of vector of 1 corresponds to the number of examples. So in the end, you should have a vector of 1 by 2 in the end. And so you time a 1, 1, 1, 1. This number of elements is n dot product. So 1 by n times n by 2 becomes 1 by 2. Two things. So you basically do an inner product, the row vector and column vector, times 1. Times 1 means doing nothing. So you basically are calculating the sum of the first column. Sum of the first column going to the first vector. Sum of the second column going to the second vector. And take a look at logistic regression. When we calculate the bias, we are doing exactly the same. So actually, we are taking this part, but without the negative sign, we are taking this part, sum all over the errors, but in there we only have 1 column. And now we have 2 columns, but basically we're doing the sum of each of the columns and put them together. So now, when we do that, it's a numpy.sum, the error of the output layer across the axis of 1, which is doing the column sum, if you remember. With axis is 0, it's vertical. Doing the vertical sum all over the column, so it becomes T number of elements. And then we purposefully reshape to have row 1 and column whatever you need. So 1 by 2. So we purposefully make sure the shape is a row vector. So if we see for the bias vector of the output, gradient for the bias of the output is calculating the sum, column sum, and reshape it to be a row vector. And after doing this is actually doing something of the weight update, right? But take that part of the weight update and define it as a gradient. Then when you do the weight update, you don't have to do that part. You simply substitute the gradient to that weight update. So, it's not actually gradient, but we're repurposing part of that code to say this is gradient for the bias, that maps with the gradient of the matrix. So after we do all the gradients for the weight matrix and the bias vector, then we follow the same formula for the weight update. So when you get to the step 1, weight update for the output layer minus eta times the gradient. Weight update for the bias of the output minus eta times gradient. Minus eta times gradient minus eta times gradient. Just the corresponding gradient. This gradient comes from here. That bias gradient comes from here. 2.1, 2.11, 2.12 maps to 3.11, 3.12. Kind of symmetric structure. Now you see why. And once you have the weight updates and bias updates, you simply update it. And the update process is also 4 steps. When you have these update terms, delta is weight update, delta W, weight of the output, delta bias of the output, delta weight of the hidden, delta bias of the hidden. When you update them, update the weight of the output plus equal. Now we don't save that middle step anymore because it's too much. It's too much to manage. So we simply add on. This means to add additional part to the original value and then replace it. That's a simplified code for Python. And do the same with bias, but make sure, for these lines, this part should be exactly the same as after the delta. This is for debugging purposes. Okay, now, so that completes one loop. Before you finish that loop, you also calculate cost. So to do the cost, you need to do a forward prop. But can you reuse the activation function of the output that you calculated previously? No, you shouldn't, because now the weights have been updated. You have to redo the forward prop. So that's why we redo the forward prop here. We only care about the activated function of the output layer. We discard all the else, and we calculate cost. We store the cost, then we move on. That's all. After training for a few epochs, then we use the most updated weights and biases, and for different layers to calculate the accuracy, or we calculate accuracy in the middle as well. Yeah, calculating accuracy requires a differently processed Y graph truth matrix, and the tutorial, the video tutorial, as well as the demo explain all of these. You can read them. Why? It should be understandable. Save the accuracy and save the cost function, and then continue to the next loop. All right. So that is not this one. That's the complete loop process. Any questions? Any questions I can explain a little bit better? Great. Oh, yeah. Okay. Which? Oh, which is the 2 textbooks? At the coding level, for sure, it's the PML. That thicker book. Not as organized, because that's why I make these graphs. I guess the best starting point is these graphs, and then if you can map, different steps, the black headers correspond to the headers in the codes, different sections, and sub steps. There are sub steps over there, but this is not there. The blue part is the, I guess, formula by using the notations. It's not there. Formula by using the matrix is not there, but these formula is very close to the codes. And these gray codes are what's in the Python demonstrations. So if you can, when you review that class demo or review, watch the video or follow the video, if you know at which step of that implementation match to which step of these, you master the process, and then you can go back and forth. So that's, yeah. In the book, you'll get lost. That's why I make these. Yeah. All right. One thing to point out is the cost. So previously in logistical regression, the cost is by using, there are two ways to calculate the cost. One is to use the cross entropy, the more complex formula, which has 1 minus y times something, and the easier way is to calculate the squared, sum of squared error. Calculate error and calculate sum of squared. Both will produce the cost function, and when you plot those two lines, the line looks exactly the same, but the values are different because one is the log likelihood, the other is actual sum of squared. Conceptually, they are the same, but the numbers get large, right? When you calculate log likelihood, log of 0.1 is 10, and when you take the negative, it's negative 10. So over time, you add more log likelihood to it, it becomes negative 3,000. It can get large, although over time it becomes smaller. But an equivalent way to calculate costs, which makes graphing much easier to evaluate, is to calculate the average cost. So what's the average cost? Is cost per training example. So you use the old cost formula and divide it by a number of training examples, which is n. Divided by n, you get a much smaller cost function. It can go as little as 0.01 or something like that. Doesn't mean the error is getting smaller, but the scale is changed, right? Because you calculate the average. It doesn't change the learning process whatsoever, but it just makes it easier for for making the plots. So that's why at first, before regularization, when I calculate the cost, I stick to the old formula. Let's see. So the cost, this is log likelihood cross entropy. It's more complex formula, but this cost is the total cost of the data set. And the cost can be, over 10,000. And later, when I move on to, mini batch and L2 regularization, I use, the cost can go from over 10,000 all the way to a couple hundreds. So graph becomes clunky, but so beginning with the regularization, when I calculate the cost, I calculate the cost the same way and I divide the cost by the number of n. It's much smaller scale. When you make the graph, it's average 2 point something reduced to, 0.5. So graph-wise, it's much easier to see. It doesn't change anything whatsoever. But if a question asks you to calculate average cost, you divide it by n. Otherwise, you don't divide. So it makes no qualitative sense. Qualitative difference, no difference. I think that's as far as the homework goes, right? You understand the forward process. You know how to define that custom function to use it. You understand the backward process, understand the cost function and average cost. You already know how to calculate the accuracy, you know. So and the epoch process, the learning, the for loop, and that's it. That's for homework. So start homework 3 as soon as possible, and finish early. I would say more than likely you'll face some errors, and it will take some time to get over them. So start early, because the amount of code that you have to copy is just exponentially increased. It's more error prone. So and be super careful when you type. Better is to copy paste, but adapt the numbers, adapt some of the names of the data set names, adapt those for the homework purpose. Do more practice. Okay. That's it for today.